Hello, good morning. How's everyone doing today?
Hey, Professor. Good, and you?
Hi, good. Thank you. So how's it going with preparing for the midterm? Yeah, I want to remind you to make sure you work on the practice exam. Also, a little bit suggestions for making best use of your time when studying is there are only several topics we cover, right? We talked about constant acceleration motion. There are a series of problems on that. Motion in two different directions, right? You look at projectile motion, X and Y directions separately, and you have dynamics, mostly Newton's second law, because Newton's second law has all of those applications. Newton's first and third law are relatively simpler and quicker. So go through these topics one by one, and in every topic, make sure you do a few problems and check your own understanding. If you're doing well, move on to the next topic, and then move on to the next topic. So just budget your time well when preparing for the exam, okay? Right, so today we will continue to talk about energy transfers. Picking up from we left off, we said, okay, conservation of energy tells us if there is a change in the energy of your system, that simply means that there is some energy transfer. Either energy has been put in or energy has been taken out. And how do we calculate that transfer? Is through work. So this is what we're going to discuss today. So we're going to study how to calculate work, and then we're going back to conservation of energy to put it back into the equation to see how work is related to the energy transfer. We say work a lot in our daily language, but the physics term work is different. Although it kind of involving a force and labor intensive, right? So doing work. So in order to have a physics term work, you have to apply a force and you have to apply that force over a displacement. Then you have done work. Noticing this is not the most accurate definition we have so far. Eventually, we will improve our definition to the ultimate expression. But right now, this is simply a preliminary definition. Okay, so it says that you're pushing a shopping cart, you push it for 10 feet. All right, so you have done work using the force you have exerted, multiplied by the distance that the car traveled. And that's the work that you have done on the cart. What about the unit of work? So we can do the dimensional analysis. The unit of work is equal to the unit of force times the unit of the displacement. The unit of force is newtons and the displacement is meters. So we have seen this before. We have seen Newton times meter is also the unit for kinetic energy or potential energy, and it's also joules. Is this a coincidence that work shares the exact same units as energy? Or is that something you might expect? Same units as the one we had for energy. Is this surprising or pretty much understood? What are your?
I don't think it's too surprising because I think it just kind of makes sense that work and energy would have the same units. That because like it's getting something done, and by the definition, I think it makes sense when you refer to doing something over a distance. Both kind of make sense to me that way. I don't know. Could be wrong though.
Right. We said it's getting something done. what does it do? We're saying, oh, work is really just changing the energy of the system. We said E final minus E initial is equal to E in minus E out. This is done through work, okay? So it's no surprising that work and unit and energy has the same unit, okay? But we prefer as a sort of a convention, we will call the unit for work as Newton meter, Newton times meter. But when we talk about energy, we like to say it's joules. It's just a convention because work is distinctly force and times displacement. So we just refer to the unit for work as Newton meters. Let's improve upon our definition because our original definition doesn't take into account, then you can apply the force in different directions. The physics term does work. You have to have a displacement along the direction where the force is applied. For example, if you have a force pushing the train forward, then this force does work. The normal force is perpendicularly upward, and there is no displacement in this normal in the normal force direction. The displacement is perpendicular to this force. So this one does not do any work. There's no work. So seems like to improve our definition, we need to account for only the part of the force that is along the displacement vector, right? So if you have a force that's in the diagonal direction, dragging something, you know that, okay, if it's moving forward, only this component does work. The perpendicular component does no work. So here you have no work, and here you does work. So you need to look at the component that matters. So we realize, okay, if we wanted to look at the component that matters, the x component of f is f cosine theta if this is at an angle theta with respect to the horizontal direction, right? So only the horizontal force, the horizontal component of that force does work. The vertical one doesn't do any work. So when we do the calculation, we should use f cosine theta times the displacement delta r. And at this point, we realize, wait a minute, because of our, so this part is math. You realize that looks very similar to something in math that's called a dot product or a scalar product between two vectors. Because f times cosine theta times delta r, this whole thing is a scalar, meaning that this whole thing is just a number. Work is just a scalar, okay? It does not have a direction. It's like energies. It's not a vector. It has only a magnitude, a number. But that is equal to the vector f force dot into displacement vector delta r. So this is called a dot product or a scalar product because it gives you a scalar. So how familiar are you guys with dot product? Have you seen or done this in math class already?
I think at least for Calc 3 students, we've already done it.
Okay, all right. I've seen some chats that yes, very good. So we can do a quick review relatively fast. So let's do some quick review on how to do dot products. But if you haven't done this, that's okay. We will go through the definition as well. A vector dot product is, for example, C is equal to A dot into B, okay? Then how do you calculate this dot product? You can use the magnitude of A times the magnitude of B times cosine the angle between A and B, okay? For example, if A is here and B is here, and let's say they have a 90-degree angle between them, and A has a magnitude of 5, B has a magnitude of 3, then you do 5 times 3 times cosine of 90 degrees. So this is a definition. And A dot into B simply becomes 15 times cosine 90. It turns out cosine 90 is 0. So it turned out any vectors that are perpendicular to each other will give you a 0 dot product, okay? So that also shows that if you have a force perpendicular to your displacement, then the force does no work. There's another way to calculate the dot product is to multiply the component by component. So A is a vector, so it can have 3 different components. In the Cartesian coordinates, it can have as X and Y and Z component. So the same for B. So when you do A dot into B, a dot product, you do the X component of A times X component B plus the Y component of A, Y component B, and the Z component of A times Z component of B. You do a component times component kind of operation. Whichever you use, this equation or this equation depends on what your information is already given to you. Whichever is easier depends on the situation. If you use a vector to dot onto itself, then you get this magnitude of this vector squared. You can see that a squared is ax squared plus a y squared plus a z squared. Okay, we already know how to calculate the magnitude of vector is taking the square root of all this component square added up. Let's take a look at a concrete example. So let's say A is given like this, is 3, 4. Now this notation means it has a 3 component in the X direction and has a 4 unit length in the Y direction. So 3I hat plus 4J hat. B is purely in the X direction, so 2, 0. So 2 units, right, in the X direction and 0 unit in the Y. So how do you find C as in A dot into B? Well, you just do it, you can do it 2 ways. If you do it component by component, you multiply the component together, 3 times 2 plus 4 times 0, you get 6. Or if you do it the other way around using the magnitude of A. So the magnitude of A is the length of A, which is 3 squared plus 4 squared and square root of that, which is 5. And the magnitude of B is simply just 2, right? Because there isn't a Y component. So 5 times 2 times cosine the angle theta. Again, if the information that's given, you don't have theta, you have to find it yourself. So in this case, I know tangent theta is 4/3. So I know theta is 53 degrees. So you can find theta and plug it in. You get C is also 6. So you can see that if your information is given to you like this, it's probably easier to choose this expression to find C. But both ways could work. And dot product will give you a scalar and return a scalar for you. Let's quickly check what we have learned with this particular question. I don't think we need to discuss, so quickly take a look at this, and when you're ready, you can put in your vote. All right, let's go for another 10 seconds. Any last minute vote? Okay, all right, I'm going to close this. Okay, so we have a majority of agreement on A, and this is not Doesn't involve much calculation at all. So you can see that was asking about the dot product between one vector. This is a unit vector, simply has a magnitude of 1, the I hat. With a vector A, they give you the components, the X and Y, Z component. So which one do you want to use? Do you want to calculate C using A times, so if I'm calling this A, this is my I hat, cosine theta, or do you want to do AX, IX plus AX, IY plus A AZIZ. So which one do you want to use?
The second equation.
Yeah, second one, that's most straightforward. So you can see that if I simply multiply the component together, I simply get 2 plus 0, because these two are zeros, and the answer will be 2. Okay, so it's really just a direct application of a dot product. Very good. All right, so we did a really brief review on the dot product, and let's see, and then we come back to work and using dot product to represent the definition of work. So here we have a more accurate definition. Okay, our definition has been improved because we have taken consideration of the force could be at a different angle. So work is defined to be the dot product of the force vector and the displacement vector. Now, when you want to calculate it, you either use the force magnitude times delta R magnitude times cosine theta, the angle between the force and the displacement, or you do them component by component. Just like the math, we have 2 methods. So now here's a question. Any guesses? Can work be negative? Do you think we can have negative work?
I think we can, just because of it depends how we define our directions, right? Kind of like in the physics problems that we've done, that if like you define y as positive, y is going down, gravity will be positive, but if you do it the other way, it'll be negative.
I see. So here when we have, well, earlier when we had vectors, we certainly could have negative vectors. If you define to the east is positive, then if you go to the west, and that's negative. But work is not a vector, it's a scalar. It has only a number. Can that also be negative? And how could it be negative?
Yeah, like if cosine is more than 90 degrees and less than 180 degrees, I mean, sorry, not 180, 270 degrees, our vector, our scalar returned would be negative, because
Yes.
the other f and change in r are going to be positive because of like the absolute values and the magnitude.
Excellent. You can see that from the math expression. Simply take a look at our expression. This is all positive, it's a magnitude, but cosine could be negative. So work should be able to have a negative value. Very good. We can simply see that from math. Well, let's see if we can come up with a concrete example where, what does negative work mean? What does it mean in real life? So you lower a block of mass down for a distance at constant speed. Again, I want to highlight constant speed. Whenever I say you see a constant speed, you know that acceleration is 0. So all the forces should be balanced. Okay. You hold the book and you lower it down. Then the book by your hand, the work done by your hand on the book is, okay, so remember to use our definition, force dot into displacement, which is force magnitude times displacement magnitude cosine theta. The angle between them is the work done by this force. All right, so I will give us a minute or two to have a discussion here in the breakout room. So make sure you take a screenshot before you go accept your breakout room invitation. So all right, open it up. Hello, Arturo, Brian, Jordan, and Marcus. I'm visiting this room today. Again, I'm not looking for an answer already, but mostly let's have a discussion. What do you think the first thing I should be doing? How do we get started?
I'm looking at maybe what the force quantity is, since we know acceleration is 0.
Mhm.
If acceleration is 0, wouldn't it make the whole thing 0? Because F equals ma, and then 0 wouldn't make it 0. The force would be 0. So then wouldn't it make r and cosine theta 0 as well?
So F net equals ma. You're right that acceleration is 0 will make all the force go to 0. But now we're not looking at all the forces. We're looking at only the force down by your hand. So there's this book, right? There's this book. And how many forces is acting on the book?
2, your hand and gravity.
Yes, gravity and from your hand. And we really just interested in this one because that's what the question is asking us. So now, which means if the net force is 0, acceleration is 0, we need to figure out the magnitude of the force by hand. And the force by hand is equal to what? So if the net force is 0, net consists of 2 forces. One is a force by hand, one is gravity. Your force by hand supporting the book is upward, gravity pointing down. So the magnitude of the force by hand is equal to, is it equal to the gravity of the book? Is that right?
Yeah, it should be gravity then.
Yes. So we now figure out this is a force by hand is mg and pointing up. All right. And you have lowered your book down for it's going downward, right, for a displacement of h. So let me plug in numbers. I know this force by hand is mg. The magnitude of your displacement is h. And what is the angle between them? So one is pointing up, one is going down. And what is the angle between them? Theta is equal to 180. Very good, Marcus. So it's cosine 180. 180 of cosine is -1. So you get negative mgh. So indeed, we have done negative work here, right? All right, I'll see you guys in a little bit in the main session. All right, looks like I gathered the majority of the votes. 10 more seconds and then we'll take a look at it together. Okay, all right, any last minute vote? I'm gonna go ahead and end this. All right, looks like B and C are equally popular. A actually has the majority of the vote. So I'm guessing the A is, well, if you vote for A, the thought might be, reasonable thought behind this might be, well, your acceleration is 0. Possibly, maybe you haven't done any work. So any thoughts and discussions on that, about this question?
I didn't particularly think that it was A because A, the work being 0 kind of didn't make sense to me because you are moving downward and gravity didn't like just stop working. So there's something in P, there's something pushing the book downwards, but you with your hand are also kind of slowing down the gravity, the acceleration in a sense to match it. So I think you have to be doing work on the book. So I don't think it can be 0.
I see. Okay. The work done by your hand. Okay, so by your hand. So there's this book. So there are 2 forces that you said. One is gravity, always down. And if you're holding the book, you lower it, you must be supporting the book and going down like this, right? So if I have a book, I'm lowering it like that. So the force from your hand will be pointing up, right? The gravity is mg. And do we know, if we want to find the work done by your hand, we just go to the definition, work done by your hand is the force by your hand dot into the displacement. Now we need to know the magnitude of this force. We need to know the magnitude of the displacement, which is given. We need to know the angle between them. So because that is the definition of work. Do we know the magnitude of this hand, the force from the hand is equal to, what is the magnitude?
mg.
Mg equal to gravity, right? Because they add up to be, the net force is the force from the hand, if you define positive to be upward, minus the force from gravity is 0 because they have 0 acceleration. So they have to cancel gravity. So now, the constant speed is really just a way to tell us what this force is, which is mg. And what is delta r? R is h. Delta r is going which direction? Going downward. We're lowering it downward. So this is delta r. And the force by your hand is up. What is the angle between them? This is one vector. This is another vector. What is the angle between them?
180.
180 degrees. Very good. Thank you, Jacob and Berenice, for answering that. And it's cosine of 180, which is -1. So you get negative mg h. So it's C. Okay, C is correct. Now let's see what A and B represent. B represent, if you were to do, well, it seems like if there is a force doing work for H, but in the same direction as your displacement, then this is what we are calculating. That turned out to be the work done. Do we have such a force pointing downward? Is mg? Yeah, this is work done by gravity. Work done by the gravitational force. This is work done by hand. And what would this be? If I had asked you, what is the work done by the net force? Then you would say 0 because you see net force is 0. Okay. but there's the work done by gravity is positive in this case, work done by hand is negative in this case, right? Another question. So further help us understand, okay, in what case you get positive, in which case you get negative, okay? So here we have 4 different scenarios. We wanted to rank the work done by these forces from the most positive to the most negative, okay? For example, if it's negative 100, it will be more negative than negative 50. So that's what I mean by most positive to most negative. We may have 100, 50, 0, negative 50, negative 100. So most positive to most negative. Okay. So, and the displacement in this case is to the right, giving it to the right. So let's go ahead and rank these different scenarios. I'll give you a little bit time to discuss with the breakout rooms, and then we can come back for a discussion. Take a screenshot before you leave so you have access to the question. Hello, everyone. Hi, Jason, Lee, and Musa. How are you guys doing? And let's take a look at this together. We'll have a discussion. We may not be able to come up with the ranking right away, but can we tell for now which one would be the most positive? If the displacement is to the right, which one is the most positive? So it's the force that is.
Is it C?
Is a C, yeah, the one that's all of the forces is in the direction, all of its components is in the direction of the displacement. Yeah, very good. C would be the most positive. And you can see that, well, if we establish that, we kind of already ruled out the incorrect answers. But let's continue to try to figure out them one by one. C is most positive, and next coming up, is there anyone that is 0, give you 0 work? The 0 work would be if the force is what? Perpendicular to the displacement. A would be 0, yes. So this is 0 work. This is most positive. And B and D, you can kind of see it's all in the opposite direction. It's to the left, right? B is completely to the left and D is to the left and at the same time upward. So between B and D, we know it's both of them will do negative work. Which one is the most negative? It's the most negative, we're going to put it at the end, right? So your ranking is C now, A now, and then between B and D, which one is the most negative? Meaning most negative, meaning all of its component is 100% in the opposite direction of the displacement. Very good, Jose. It is going to be B, 100% to the left. And D is also negative, but you can see it's only a component of that is to the left. Another component is perpendicular, and this one doesn't do work. This one gives you a negative work, but it's not as much as a negative of the B. Excellent, good job, everyone. I'll see you in a bit when we return to the main session. All right, so let's run it for 10 more seconds. If you haven't voted already, please do so. Okay, any more thoughts and notes you want to put in before we close it? All right, okay, I'm going to head and end the poll. It looks like we do have quite a strong agreement on choice C. Okay, all right. So A, B, C, D, we have 4 different little scenarios. So by looking at these, which one looks obvious to you that, well, let me pick out the most positive first. So which one is the most positive?
C.
It is going to be which one?
C.
Eric, yes. So we see also there's an answer in the chat says it's the C with our displacement going to the right. If it's most positive, you want all of the force is going to the right. So that's going to be the most positive. So all of the components. So this one would be more positive as if it's were tilted a little, it's not as positive, this one. So C is the most positive. So this is most positive. Okay, now there isn't anyone that is sort of diagonally upright. So they're either perpendicular or sort of to the left. Then from the rest of it, A, B, and D, which one is 0? Because I know from positive to negative, that in the middle is 0. So which one is 0? It's going to be A, thank you, Elaine, because it's perpendicular, very good. Now, if the force is perpendicular with a 90-degree angle, cosine of 90 is 0. This force does not do work. Okay, this is 0. So C, A. So between B and D, which one is most negative? Which one is most negative?
B.
B, excellent. The one that is 100% in the opposite direction of your displacement will be most negative. And then D is part of it is doing negative work and part of that component doing no work. So if you decompose it into X and Y component, you can see you have a negative work, but not as negative as this one. So if this do negative 50 Newton meters, this might be a negative 100 Newton meters. Okay, excellent. C is the correct answer. Very good job, everyone. So further to look on work, we have already established, what do we establish? Work can be negative. Work depends on the angle that you're applied the force on. And we looked at work for individual forces. So how do we calculate net work? Because there are many forces. To calculate net work, well, there could be 2 different approaches to this. You might say, well, let's calculate the net force first, sum up all the force first, and then look at the work done by that one net force. Or let's look at the work done by all the individual forces first, and then sum up the work. Which one do you want to, which one of these approach makes more sense to you, or do you like better? Or you feel equally okay about these two methods? Okay, well, I don't have don't get an answer. I assume that you guys feel pretty neutral about either of those methods. So which one? I'm sorry.
Sorry, to be clear, the first one is when we do the like the definition with the magnitudes and cosine, and the second one is when we do the x and y component and z component breakdown.
Oh no, sorry. This question is asking if you want to calculate the total work. You have two approaches. One is to find the total force first, and then to total force dot into displacement. Another approach is to find each individual. So let's say you have F1, F2, F3, all of these forces. Find work 1, work 2, work 3 first, and do the network being adding up all the individual work. So this is what I mean by two different approach.
Oh, so yeah, could you go over the second one more then?
I'm sorry?
Because weren't you asking like which one you'd like us to go, you would like us to tell you to go over more?
Just which one you think, oh, right away, I like this method better. But I can already tell you, both of this works. Both of this are a eligible, good method to calculate the total work. You can either do this or this. I'm just curious if any one of them feels better, you feel better about it. But we can look at a more concrete example. Maybe you can decide which one feels more natural to you. So let's go to this example. This example we have already seen, so it should be fairly quick. Okay, so you lower the book again at a constant speed. We just did that. The work done now is asking by the net force, or if I had changed the language saying that what is the total work done? What is the total work done on the book? So you can see that, well, it looks like maybe the easiest method for this particular question is to use this approach. Why? Because we already know the net force is 0. We can right away, regardless of what are the forces and what are their magnitudes, right away we know the total force is 0, right? Do you agree about that? Guys agree on that?
Yeah.
Yes.
Okay, because, thank you, because the acceleration is 0. So if I know that, then, well, if net force is 0, then the work done by this force, obviously, is going to be 0 if this is 0. So right away, you know, oh, the net force is, the work done by the net force is 0. Now, if you take a different approach, saying, well, what if I calculate the work by individual forces separately and add them together? So you realize there are just two forces here. Force 1 is gravity. Force 2 is a force by your hand, which is also mg, but pointing upward, right? The force from gravity is mgh positive. The force from your hand is negative mgh negative. We have calculated these from the previous question. So you can add up individual work and they still give you 0. Okay, so the two methods essentially give you the same result, and they should be consistent. For this problem, you probably don't notice too much a difference in terms of which approach to use. But if I chose to give you another problem, this one you probably already see. You probably realize, okay, one approach is better than the other. So you have a car driving up the hill with constant speed. Okay, again, whenever you see this buzzword, constant speed, that tells you acceleration is 0. Okay. Now, what is a work done by on the car by all forces as it moves up the hill with that constant speed? So if you were to do work by individual, adding together, now you need to consider, okay, gravity, normal force, and it's going at constant speed. I should, to balance out this gravity, I definitely have some kind of a driving force forward. Now, all of this gets very complicated, but all I care is no matter what these individual forces are, they should add up to be 0 because acceleration is 0. So my total work net is going to be 0. Okay, so the answer is 0. So whenever you have a question that the object, the speed is not changing, it's a constant velocity, meaning that the total work done on this object from external forces should be add up to be 0, which makes sense, because if there is a positive work done, then work is energy transfer. It's going to make you go faster and faster. If you have negative work done, and that's energy transfer and energy taken away from your system, you have to slow down. So either positive or negative work would have changed your energy, would have changed your speed, right? So if it is a constant speed, then that means there should not be any total net work done on the object. It should be 0. Otherwise, the speed would have been changing. Okay.
Professor.
Yeah.
I wanted to ask, for this particular problem, how come we wouldn't include the frictional force?
There might be friction too. I didn't write it because I just want to show there are so many different possible forces involved. It's so complicated, so we chose to go this method. But yeah,
Okay.
yeah, and it's and then we also said that kinetic friction is really just a ideal approximation of what really goes on between the tire. It's not a sliding, so this is more of a rolling friction, so it's a little different than sliding friction. So we haven't gone to rotational motion yet, so I don't want it to make it too complicated. Okay, but thank you for pointing that out. That's a good observation. Okay, so you might be pretty happy with our definition, but I want to further improve it, make it final, and this is final. We're not going to go any further with this. This is your final expression. I wanted to change this dot product delta r into an integral of dr, simply because, well, the force might be changing with respect to time. You don't always have a constant force. You may have a force that's increasing or decreasing. So to take that into consideration, do an integral of force dot into displacement is more accurate. But if you have a constant force, by all means, to use this expression. Okay. You can also see from this graph that F dot into dr is what is area under the curve, right? So whatever this curve is, the integral gives you the same thing. It's area under the curve. So for example, if your work is changing over time as this curve, then you can see the way to calculate work is no different. It's simply, okay, what is area under this curve? In math, you represent using integral from x1 to x2, f in the x direction times dx, the displacement, okay? So it's area, it's under the force position curve. All right, let's see if we can get this done together before we have to end here. So you have a force, this force is changing. How does it change? For the first meter, 1 meter, the force is 0. And then from first meter to third meter, there is a constant 2 Newton force. And then from 3 meters to 4 meters, again, you don't have any force. And from 4 meters to 5 meters, you have a force. It's from -2 and decreasing to 0. It's asking how much work done on the block, how much work is done by this force, complicated force. So what do we do?
We find the area under the curve of each part.
Perfect, thank you, Brian. We can find the area under the curve. Okay, so really just 2 areas, 1 and 2. What is this area under the curve?
4.
Very good.
Yeah.
What's this area under the curve?
-1.
-1, perfect. Triangle. So 4 and -1 combined get you 3. So that's it. That's the last question. All right, thank you everyone. That's all we have for today. We do not meet on Wednesday. Okay, Wednesday is your exam day. We do not have a class meeting. You can choose any 2 hours you have to work on your exam. And if you run into any technical problems, feel free to email me. Okay, and then I'll make sure to help you sort it out. And collaboration is not allowed. You can look at your online textbook and online homework. You can check our lecture videos, but do not Google the answer or call your friend for an answer. All right, have a good rest of the day.
Wait.
I'll see you guys on Friday. Yes?
Wait, Professor. So during the exam, we could open up your like lecture video and rewatch like certain parts or like look at through the PDF.
Of course you can, but it won't be very efficient. You should, if you want to download my lecture notes, download it beforehand. I don't want you to go through it, try to look for it because the exam is timed.
Yeah.
But you're allowed to do that. Yes, of course.
Okay. Thank you.
Okay. Bye. See you on Friday.
Bye, Professor. Have a good day.
Thank you and have a good day yourself.
Professor, what did you mean by we can do any 2 hours? I thought it was a specific time.
It's Wednesday from midnight to the end of day Wednesday. So let's say you want to do it from 10 to 12 in the morning or from 4 to 6 in the afternoon. That's up to you.
Oh, okay.
Yeah. Okay, Jared, you have a question?
Professor, what's your policy on missing a lecture?
So I do not take attendance, as you can see. We can't really require attendance for this kind of class. So I don't have like a penalty for not coming to lectures, but it's in your best interest to come and then make sure you follow the lectures every day. But I'm not taking any credit off if you don't even miss a lecture. So I think it's best to come to lecture if you can, but if you, for any cases, you have to miss a lecture, make sure you watch the recordings and figure out what we talked about and make up for yourself and ask me questions if you have any questions.
Okay, thank you, Professor.
Sure. Any other questions?
I was a little bit confused for this particular problem, how we deal with delta R. And I wanted to know a little bit further about what exactly is delta R.
Delta R is displacement, which
Okay.
you moved. You move to the right or you move to the left. So what is delta R? Good question. In this case, now we simply change from F dot into delta R into area under the curve. So we don't really care about what is delta R, but if you wanted to look at what is delta R, okay, so this particle or whether this block travel from 1 meter to 3 meters. So so delta R is from, okay, so 1 meter to 3 meters. So this is your delta R, is you travel 2 meters to the right. From 4 to 5 is you traveled 1 meter to the right. So that's your delta R for that particular section.
Okay, got it. All right.
No problem.
And so in this case, since it doesn't give us like specific directions about like, for instance, left is the displacement or right is the displacement, we assume that the correct displacement in the positive direction is to the right, correct? Hope that makes sense.
Well, we defined from 1, 2, 3. Well, that is a positive, which is already defined.
Right.
And you can see is, well, I know that at 1 meter, there's a force acting on it. From at 3 meters, there's still the same force acting on it. So, so you know at least the position, the object must have passed by a 1 meter position and a 3 meter position. Does that make sense?
Yeah. Okay.
Yeah, so the area under the curve just doesn't, you don't have to worry too much. Okay, exactly how it is moving.
Right.
You just look at the area, right? That's a graphical approach.
Right. Okay. Okay. Well, thank you, Professor.
You're welcome.
Have a good day.
Thank you, you too.